Welcome to YouTube channel Scientific underscore Math. This is third lecture on eigenvalues and eigenvector. In two previous lectures of eigenvalues and eigenvector, we studied about the definition of eigenvalues and eigenvector, graphical representation of eigenvalues and eigenvector, and we have also studied the eigenvector x cannot be equal to 0, and we solve example of matrix order 2 cross 2 in which we found the eigenvalues and eigenvector for that matrix. Okay, so I will provide the link in video description, um, both lectures. For in this lecture we study the procedure for finding the eigenvalues and eigenvector of order 3 cross 3 matrix, and we solve example in which we find the eigenvalues and eigenvector of matrix of order 3 cross 3, and in which we uh, study two cases, non-zero eigenvalues and non-zero eigenvalues, and here we again say eigenvector cannot be equal to 0, and in this case when we say zero eigenvalue, and here the eigenvector cannot be 0 in any case. Okay, so then we also represent the eigenvalues and eigenvector graphically. So let's start today lecture. Okay, so first we discuss the procedure for finding eigenvalues and eigenvectors. Okay, first we step we have, that is first find the eigenvalues lambda of A by solving this characteristic equation. Okay, so here this is the lambda and this is the identity matrix and this is the given matrix A. Okay, so number two we have, for each lambda that we have solved by getting by solving this equation we get the lambdas. Okay, so for each lambda find the eigenvalues. Here we can see that eigenvalues cannot be equal to 0. Okay, so for each lambda find the eigenvector by finding the basic solution to this characteristic equation. Okay, so second step is we will find the eigenvector to each value of a lambda. Okay, third step we will verify this operation, that is to check that whether our eigenvector is correct or not. Okay, so we have an example, and let the matrix A is equal to this one, and this is the square matrix of order 3 cross 3. Okay, so let's solve this, and here we have to find the eigenvalues and eigenvector. Okay, solution. First we find the eigenvalues of A by solving the characteristic equation, and here this is the identity matrix and this one is the given matrix A. Okay, so after substituting we get this one. Okay, here we have a shortcut trick to find the to solving this matrix. Okay, like we have this one. This is the lambda cube minus trace of the matrix A into lambda square plus sum of minors along the diagonal minus the determinant of the matrix A. This one. Okay. So what is the trace of the matrix A? Trace is the sum of the elements along the diagonal, that is 5 plus 14 plus and that is 6. Okay, and we know that how to find the determinant of this matrix A, and the last thing is sum of minors along the diagonal. There will be also lambda. Okay, sum of minors along the diagonal, and how we can find the minors along the diagonal I will show you. Okay, so trace is equal to this one, that is the trace of the matrix A is 25 and the determinant of the matrix A is 500. Okay, so next we have to find the minors. Okay, here we have the first minor, that is M11, in which we leave the first row and first column. Okay, so here we can see that this is the first column and this one is the first row. So after leaving the first row and first column we have elements 14, 2 minus 8 and 6. So, and by solving this we get 100. Okay. So for minor 2 along the diagonal M22, here we leave the second row and second column, and we get this one. Okay. So for third minor, we leave the third row and third column, and after this one we get this one. Okay. Now we sum up all these minors, and after summation we get 200. The sum of minors along the diagonal is 200. Okay. Now substitute uh, all these in this equation. Lambda cube a trace we have found, and sum of minors, and determine. Okay, so after substituting we have a equation, this one. Now we solve this equation, and okay, so after simplifying this equation we get this form: lambda minus 5 into lambda square minus 20 lambda plus 100 is equal to 0. Okay, so this is our first equation, and after solving this equation, or after putting this one is equal to 0 and this one also equal to 0, we get this one, and our first eigenvalue, that is 5. Okay, so now again by solving this quadratic equation we get the lambdas that are equal to 10, 10, and this is the multiplicity of 2. We know that what is multiplicity. Multiplicity is the repetition of eigenvalues, number of repetition of eigenvalues. Okay, so solving the equation, we found that eigenvalues are lambda 1 is equal to 5, 2, 10, and 3 also 10. Okay, so here we notice that 10 is a root of multiplicity 2, due to, because this equation is equal to this one, and here is the power is 2, therefore lambda 2 is equal to 10 is an eigenvalue of multiplicity 2. Okay, so uh, next we have, now that we found the eigenvalues for A, yes, that are the lambda 1, lambda 2, and lambda 3, that are the eigenvalues of the matrix A. Okay, now we can compute the eigenvectors. Okay, so by definition, x is equal to lambda, eigenvector is equal to x1, x2, and x3 is an eigenvector of the matrix A corresponding to an eigenvalue lambda if and only if x is a non-trivial solution to this equation, means non-zero solution to this equation. Okay, so let's find the eigenvector. Okay, first we find the eigenvector corresponding to the lambda 1 is equal to 5. Okay, so substitute this into this equation. What is this? That is lambda into plus minus a into x, which is equal to 0. Okay, first we put over here lambda 5. Okay, so here we have the equation by substituting the identity matrix, matrix A, we get this form. Okay, so simplifying this one, we have this equation, and we write the augmented matrix to this system. Okay, so we have the augmented matrix corresponding to the this system. Okay, so now we uh, reducing into row echelon form this matrix, augmented matrix, into row echelon form. Okay, so after simplifying or doing some calculation, we will get this form, and here we can see that. Okay, again, again we write this into Ax is equal to b form. Then we can see that the column 1 and column 2 is pivot column. Here we have, this one is the column 1, this one is the column 2. So both of these columns is are pivot column, means in the diagonal entries are non-zero. But okay, so these columns correspond to variable x1 and x2. Yes, x1 and x2, making these the basic variables. So the pivot columns making the variable x1 and x2 basic variable. But column 3 we not the pivot column. Here we can see that this is 0. The diagonal entry of the column third is 0. This means this is not a pivot column. So which means x3 is a free variable. Okay, so what we do when any free variable is appear, so we suppose let x is equal to any arbitrary constant that is k. Okay, so then we solve this first multiply the first row with this one and the second row with this uh, vector that is the x eigenvector we can say. So after simplification we get that the x1 is equal to 5 by 4 k, and here we substitute or replace x3 with k. Okay, so x3 is because x3 is a free variable. Okay, so next again x2 is equal to minus 1 by 2 into k. Okay, so let's write up them in this form, and x is equal to this form, and then we take common k from these values. Okay, so if we multiply this vector by 4, here we can see that if we multiply this vector by 4 to remove this fraction, okay, to simplify them. Okay, so if we multiply this vector by 4, we obtain a concise solution to the system as given by. Okay, here we have the concise solution. Okay, so here we know that and k is belongs to the real number, and okay, so this gives the eigenvector for lambda 1 is equal to 2. Sorry, lambda 1 is equal to 5. Okay, so here we have the first eigenvector corresponding to the uh, eigenvalue that is lambda 1, which is equal to 5. Okay, so notice we can't let k is equal to 0 here because this would result the 0 vector, and eigenvectors are never equal to 0. Okay, so on uh, other than this value, every other choice results in an eigenvector. Okay, so here we can't take k is equal to 0. We can take any value other than this one. Okay, so other all the other choices give us an eigenvector. Okay, so now we have the last step is we will verify whether the uh, our calculated eigenvector is correct or not. Okay, so we substitute over here a and the eigenvector, then we will see whether this multiplication whether equal to this one or not. Okay, so after substituting and multiplying, we get this one, and we take 5 common from this one, and we can say that we can see that this is the our calculated vector eigenvector that is x, and this is our eigenvalue. So the eigenvector is correct. Okay, so let's we have the graphical representation of this one. This is the uh, x coordinate, this one is the y coordinate, and this one is the z coordinate. Okay, so this is our vector x. Okay, this one that is the 5 minus 2 and 4. Okay, okay, here we have the x is 5 and y is minus 2. This one is the minus 2 over here, and this z is 4. Okay, okay, so this one is the our this one is a vector x, and after multiplying the vector x, this is stretching. Now we can see that the vector is stretching after multiplication with lambda. The vector is stretching and in the same direction. eigenvector is stretched in the same direction. Okay. So here we have and multiply the eigenvector with eigenvalue, that is the lambda. The eigenvector is stretched and in the same direction. Okay. So let's find other eigenvectors corresponding to other eigenvalues. Okay. So for lambda 2 is equal to, for lambda 2 and lambda 3, that is equal to 10. Okay, again we do same procedure to find the eigenvalues and eigenvector. Okay, so after substituting and simplifying with the matrix, and we write up the corresponding uh, augmented form to this system, and then we row reduce into this form, and after reducing this into row echelon form, we get this one, and again we write up in the ax is equal to b form, and here we can see that we have two free variables corresponding to each column, column 2 and column 3, because column 2 and column 3 is not pivot column. Okay, so this means x2 and x3 is free variable. Again, we suppose or let x2 is equal to k and x3 is equal to t. Okay, so after simplification, we multiply this row with this one, and after simplifying, we get x1 is equal to this one. Okay, so then we write up in the vector form, and we take over here first k common from this one with, and then t, because we have uh, two constant to k. Okay, so where k and t cannot be, k and t belongs to the real number. Again, notice that we can't pick k and t both equal to 0, because this would results in the zero vector, and eigenvector are never equal to 0. Okay, so this gives the two eigenvectors for lambda is equal to 10, as that is the eigenvector x2 and eigenvector x3. Okay, now we again verify whether the calculated eigenvalues are correct or not. So I will do this one for the eigenvector, this verification for this eigenvector. Okay, so to check we verify this equation, and okay, so here this is the matrix A, this is the eigenvector x3, and after multiplication we get this one, and then we take 10 common from this one, so this is the uh, eigenvector, that is the x3, and this is correct. Okay, so this the eigenvector is correct. Okay, so here we have, it is important to remember that for any eigenvector, x is not equal to 0. However, it is possible to have eigenvalues equal to 0. So we will also solve example when the eigenvalue is 0. Okay, so we have the graphical representation of this eigenvector. Okay, so this is our eigenvector x, that is okay, so that is minus 1, 0 and 1. Okay, so after multiplication this eigenvector, we can see that this is stretching. This is the lambda into x, means when we multiply this vector with 10, we get a stretching in the same direction. Okay, so eigenvector or the vector is stretched in the same direction as of x. Okay, so this mean the eigenvalue after multiplication with the vector x, the vector is stretched in the same direction. Okay, so let's see this in 3D video. Okay, so this is our the eigenvector and x, and after multiplication with lambda. Okay, so now we will solve when the eigenvalue is 0. But again, I will say the eigenvector cannot be equal to 0 in any case, because this make no sense that the vector is 0. We have already studied this in lecture 2, and the link of lecture 2 is available in video description.